And so the next thing to do is to look for distances. And instead of just looking for distances between two parallel lines or two parallel planes or even two skew lines, we can also extend that to finding the distance between a point and a line or a point in a plane. So if you take those three types of objects, a point, a line, and a plane, and if it makes sense to find distances between them in space, we can have, you know, as many combinations as would make sense for us. So the first one is a point to a point. That's just the distance formula. So that's, I don't know if that's what even we're talking about, but I'll put the formula down for the point, the distance between 2 points. And then finding distances between other objects you may be able to find the formulas for them, but I think it would make a lot more sense if we actually did the work to find those formulas. And then that'll help us remember it a little bit better, I think. So let's say you have a point A, we'll call that x naught, y naught. Oh, I don't know if I want to use A. Let's call it P naught. And let's have another point P1. We'll call it x1, y1, z1. Then the distance formula is just going to be the difference of each of those squared, all under a square root. We've seen that before. And it's kind of like an extension of the two-dimensional distance between 2 points. And since it's being squared, the order doesn't matter. And that would also make sense that the order doesn't really matter. So I think the next thing we want to do is we want to find a distance between a point and a line or a point in the plane. And I think the book goes over both of them. They have a nice formula for the point and the plane. But either of these would be a good example, so that if we're trying to find a distance between two parallel planes, all we have to do is find a point on one plane, and then you essentially find the distance between a point and a plane. And when I mean distance, I mean, of course, a perpendicular distance. So let me see if I can get some visuals on this, and then we'll pick one that we're going to do. Well, which one should we do, the point in the line or a point in the plane? What? Point in the plane. So we'll highlight this and then talk about this on a separate page, but let me give you some visuals on the rest of them. A point in the line, it just means you have a point and then a line, assuming the point is not on the line, because if it was on the line, it would be 0. And you want to find the vertical distance, or the perpendicular distance. Two parallel planes. You have two planes. The normals are collinear, parallel. And so you would have a vertical distance there as well. The two skew lines is kind of weird. Well, a point in the plane. Wait, that's the same thing as that one. A line in the plane and two parallel planes. Wait, and there's the repeating stuff. Oh. Okay. What am I going to erase? So a line and a plane, two parallel lines that actually two lines of direction vectors are going in the same direction, maybe opposite direction, but they're collinear. So again, we're looking for the vertical distance. Two skew lines is a little bit weird, but here's what happens when you have two skew lines. When you have two skew lines, they don't intersect, right? And what happens when you have two skew lines is that the skew lines, and you have to somehow find this, the skew lines actually lie on two parallel planes. Didn't make that look parallel. Let's see if I can make it look parallel. The two skew lines actually lie on two parallel planes. And when they lie on two parallel planes, it's like finding the distance between two parallel planes. Right? So the distance between these two skew lines, you can try to find the shortest distance between the two skew lines. The shortest distance is going to be that perpendicular distance between the two parallel planes that each of those lines lie on. Does that make sense? And again, to find that, you just have to find a point on one of those. You find the equations of the planes, you find the point on one of those on one plane, and then you find the distance between that point and the plane. Then that's going to be the same distance. So that's the two skew lines business. A line and a plane, it's kind of like the skew line story. You can have a plane here, and then a line, as long as the line is not, it's not going to punch through the plane, then that means there's some sort of parallel plane that the line is on. And then you would find a distance there as well. Okay? So those are like the distances that you would be asked to look for, maybe in your homework problems or somewhere else. But what we're going to do is we're going to focus on finding the distance between a point and a plane. And once we do that, maybe some of these will come a little bit easier. Maybe not, but hopefully it will. But all of these rely on the idea of projection. We're going to project something onto something else. So there's two skew lines, so that's like a point in the plane. Let's see. Well, all of these are like a point on the plane. All right, so let's do a point on a plane story. Let's figure out how to deal with that. Point in the plane. Let's give ourselves a point. And let's give ourselves a plane. I want this in purple. And then I'll just give it an equation, ax plus by plus cz. So given that I have a plane and I have the equation of the plane, what else do I know about this plane? I know one more important thing about this plane. What? What? It has multiple points. It has a million, billion, infinite number of points. It has a lot of points. In fact, we're going to randomly pick one. We can find a normal vector. That's the other important thing. And not only can we find it, but we can actually identify it. It is A, B, C. Okay, so I have a point and a normal. Any point out of the infinite number of points I can choose. I'll pick one and I'll call it x1, y1, z1. All right? Now, I don't know how long my normal vector is. I'll exaggerate that a little bit later. But what I can do now is I can kind of pick a vector here. It doesn't matter which way it's pointing. Let me see. Let me make it point this way. All right? And let me make my normal vector a little bit longer. So I have a normal vector somewhere in space, or somewhere on this line, and then I have this other vector that connects the point that I know fixed and some other random point that I'm choosing from the plane. Okay, are we good so far? Now let's take a look at these two vectors. And let's put these vectors from tail to tail. So what I want to do is I want to see this projection of one vector onto the other. Now this isn't the usual projection picture that you normally see, right? You normally see the projection going downward. So what if I just take this thing and, you know, turn it so that it looks like it's sideways? So this is our normal vector n. This is our newly made vector. Let's call it v. Do you remember what v is supposed to equal to if I were to resolve that vector? Well, not the distance. It's an actual vector, so you're on the right track. What should it be? I have 2 points, and I want to make a vector out of it. What should it be? You subtract, right? Subtract the 2 points. So it's usually head minus tail, so I'm going to take my x naughts and the naughts and have that first. So this is x naught minus x1, y naught minus y1, z naught minus z1. So that's my vector v. And I want to do this projection. Should have did that projection in a different color because I want this distance. The distance here, this distance over here, this is a scalar projection. is going to be exactly the distance that I'm looking for. So let me see. If I move these vectors around on the plane itself, and then add on those other drawings that I have, then this distance over here is exactly the distance from the point to the plane. So this distance over here, the scalar projection, is what we're looking for. This is the actual distance. That we're looking for. Okay, so what is it? It's scalar projection. It's COMP, as in component projection of the vector V onto n. So this is the notation that we would use. This is a component projection of V onto n. And you remember the formula for that? It's like a dot product or something, right? So it's V dot n divided by the magnitude of something. Do you remember what the magnitude of what? N. It's the magnitude of the vector that you're projecting onto. So it's magnitude of n. Okay? So try to see if this picture makes sense. If this picture makes sense, then you can take these ideas and extend it to those other objects. Point to a line, you know, two lines. It's essentially projecting a point to a plane or a line. It's a vector projection problem. Or not a vector projection, a scalar projection problem. All right, so let's take that and put in the values that we know. We know that V is this long big mess, x naught minus x1, y naught minus y1, z naught minus z1, and we want to dot that with n. So that's going to be the numerator. N is ABC. The denominator is the magnitude of n, so that's just a square root of ABC squared, each of them squared. So the distance here is going to be given by a big numerator. It looked like it was a dot product. It's ABC, and dot products are commutative, so it doesn't matter if I do n first or v first. And v is x naught minus x1, y naught minus y1, z naught minus z1. And then the denominator is the magnitude, a squared, b squared, c squared. Okay? Now, one more thing, though. This is a component projection. It's quite possible that this vector was pointing the opposite way, and then we're going to get the negative of this. So just to avoid the negative aspect of it, we're going to put the absolute value. The dot product is a scalar, remember? So just to make sure that it's positive, we'll just put the absolute value, and then that'll clear things up. All right. I'm actually happy with this formula right here, but the book has a different formula, and the book works this out. And so let's work this out and see if we can match the formula that they have in the book. So the distance is going to be equal to, continuing on here, let's take the dot product. And when we take the dot product, you have a times x naught minus x1. So let me just split that up already. A x naught, well, let's keep it together, and I'll split it up in the next step. I'm going to skip one of these steps. guess I'm not going to skip a step. And so I'm going to distribute, and then I'm going to combine some things a little bit separately. So what I did here is I took I distributed the A, B's, and C's, the A, B, and C, and then I split them up, and I put all the negatives on one side and all the positives on the other side, and I factor out a negative sign from all the negatives. And so I get AX naught, BY naught, CZ naught minus AX1, BY1, CZ1. Now let me remind you that N is ABC, so once we find the normal, we essentially have the normal vector. X naught, Y naught, Z naught is the point that's not on the plane that we know. We know that point. Now the issue is that X1, Y1, and Z1 is a point on the plane that we randomly chose. We just randomly chose it. It's on the plane. So we don't quite know what that is, or we can make it up. But if you think about it really hard, what is this thing equal to? Okay. Keep going. D. Yes. Because if x, y, z was a point on the plane, then it should satisfy this equation, and that should equal a D. Bam. There you go. That's the equation that they have in the book. AX naught plus BY naught plus CZ naught minus D. That whole thing became a minus D. And just to be sure that this is going to end up being positive, throw the absolute value around that. And then the magnitude of the normal. And then that's it. So that's your formula for the distance between a point, x naught, y naught, z naught, and the plane, ax plus by plus cz equals to d. So all those parameters are being used here. X naught, y naught, z naught comes from the point, a, b, c comes from the equation, and d also comes from the equation. All right? So this equation is easy enough to remember and memorize, and if we were to do a problem, all we're doing is picking those parameters from the equation and from the point, and then we'd be done with this problem. But the important part here is the process, is trying to see. Visualization might be a difficult part if you're trying to see this in 3D, and if you are having a hard time, try to see if you can actually do this with markers and pens and pencils, and then do it on your desk, where your desk could be the plane and a point can be some point in space somewhere, and try to visualize that in 3D yourselves instead of seeing a two-dimensional picture on the screen. But if you're able to do that, then those other issues when we're trying to find a distance between two skew lines, for example, or a point in a line, or a line in a plane, they would fall into place the same way. All right? Okay. I'd like to move on now. Are we good? We're good. Oh, I didn't open my text. So we're going to move on to the next section, which is trying to more visualization, more memorization almost of equations. So kind of brings you back to the idea of the conic sections, where if you have this equation, you do some stuff to it, you got to know that this equation is an ellipse, or this equation is a parabola. So our task is to look at surfaces in 3 dimensions using equations that are given to you in 3D. This is 12.6. Kind of weird that they put it in this chapter, but they put it in this chapter. So we have surfaces that we're gonna study, and we're gonna look at them in 3D. Ellipsis. Oh, I think this is not supposed to be ellipsis. It's supposed to be something else. Ellipsoid. And so what we're going to do is we're going to extend our ideas of the conic sections into 3 dimensions and then call them cool names like ellipsoids and hyperboloids, and elliptic paraboloids and hyperbolic paraboloids and stuff. Doesn't sound fancy? Yeah. That's hard. All right. We talked about cylinders already, so we can be done with that. The cylinders, remember, there's only two variables involved. The third variable is missing, so you draw the 2 variables and the axes, and then you sweep it along the third axis. But let's take a look at the others. So the sphere is an extension of a circle. So let me give the equations for these things, and then we'll give the parameters and the different ideas that are involved. The sphere is the easy one. X squared plus y squared plus z squared is equal to r squared. That gives you a sphere radius r centered at the origin. And then you know that when you move the center, you just shift the axis, the variables, so x minus something. And so if we change this into x minus x naught quantity squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. Now this has a new center. At x naught, y naught, z naught with the radius r. So this is your more general, the second equation is your more general sphere. And so this is how it would look like. Okay? So an ellipsoid, just imagine an ellipsoid being a sphere that's been stretched out in one direction or a couple of different directions. And so now imagine the equation of our ellipse in 2 dimensions and just adding a third variable to it, like we did with a sphere, from a circle to a sphere. So if we do that, it's going to be the same idea for the ellipsoid. So the ellipsoid will be x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. And keeping the right-hand side equal to 1 will help us find the intersections or the boundaries for your ellipse on the x, the y, and the z axis. So again, this is centered at the origin, so if we want to generalize this, move this out of the origin, there's another shift in x, y, z. So we can do the same similar shift, x minus x naught squared over a squared and so if we shift it the same way we shifted the sphere, then the only thing that would change would be the center point. That's your general ellipsoid. Okay, so there's no real big mystery here, change in what we've known from conic sections, because it just goes three-dimensionally. But I do want to go back to that 3D plotter that I miserably failed in yesterday when I was trying to do stuff. I found a shortcut to zooming in and zooming out, which was right in front of me. These little magnifying glasses. Oh, of course. And so I'm interested in graphing now a sphere and an ellipse, or a sphere and an ellipsoid. And for that, those spheres and ellipsoid are not functions that you can solve for z. If you solve for z, since z is squared, there's a positive and negative part to it. And if you look at it, there's positive and negative parts to a sphere, the top half and the bottom half. And we'll dig into that a little bit later on. But for now, let's look at this just as a relationship between x, y, and z. And for you to be able to draw things with relationships that are not solvable in one variable, you generally want to use what's called an implicit relationship or implicit surface. So here's one that's almost like the one I want. Let's just make a simple sphere for now. X squared plus y squared plus z squared is equal to, let's go to 4, so that it has a radius of 2. And obviously you get a sphere, right? So this is surface number 1. If I do another surface, and this time, can I do another surface? Oh, I can't close this. I need to open up another surface. And this time, let's change the parameters a little bit. So let's divide by, for the first one, let's divide by 3 squared. Let's divide by 9. So imagine the sphere now that had radius of 2. Imagine taking the x, the positive and x-axis, and stretching it out to 3. That's the square root of 9, right? For the second one, let's divide by 4, so it'll stay there. And for the third one, let's divide by 1 for the z-axis. So imagine the sphere, it gets stretched along the x-axis to go hit the 3. In the y-axis, it'll remain at 2, and in the z-axis, it'll shrink down to 1. So I'm not getting the whole picture here, and here's where I get to zoom out now. A little bit more, one more. It doesn't, looks like a flying saucer. All right, so what I need to do here is I need to increase the to make it smoother. So now if you look at the x-axis, it got stretched along the x-axis. Can you guys see that? I can't even see that from the screen. It just looks all dark. It gets stretched along the x-axis, along the y-axis it's the same as a sphere, and then along the z-axis it got squished down a little bit. So it's not a very good comparison, but it's hard to visualize. So let me see if I just take this picture and put it in our notes to see if it'll get any better if you look at it later. pi box around the plot. So this is your x, your y, and your z goes up, and you have a ellipse, x squared over 9 plus y squared over 4 plus z squared is equal to 1. And then you have a sphere, x squared plus y squared plus z squared is equal to 4. All right. So oh, maybe that's why the sphere didn't look like it was big enough. Oh. That was, yeah, something didn't quite fit right there. Let's see. Is that better? Still can't see. Oh well. I think this is a more correct picture anyway, so let's copy this one. If I can get it straightened out. All right, got something. So, that's a sphere and an ellipsoid. The next ones are paraboloids. We call them paraboloids. One of them is an elliptic paraboloid. The other one is called the hyperbolic paraboloid. So let's take a look at those and see what they mean, what they would mean to us. So what's a parabola? A parabola in conic sections is that one of the variables is squared, the other one is not squared, right? And so if we have three variables, imagine, let's think about that, where one of them is squared and then the other one is not squared. Well, there's three variables. One of them is squared and then two of them, wait, one of them is not squared and two of them are squared. So z is equal to x squared plus y squared, for example. So one of the things that they have you think about when you guys are trying to visualize this is to look at what's called cross sections. Maybe I'll try to do this by hand before I graph it. So cross sections. Cross sections, whatever this thing might look like, this thing is going to be in three-dimensional space looking like a surface. If you look at it to see how it cuts the coordinate planes, we might get some interesting insights with that. So let's see, the xy plane. What's the equation for the xy plane? So when z is equal to 0, I have 0 is equal to x squared plus y squared. Is that a graph of anything? Can this ever happen? Can you find x and y so that it's equal to 0? 0. So if x is 0 and y is 0, then this is satisfied and z is equal to 0. So it looks like this surface, whatever this surface is only going to touch the xy plane at 0, 0, 0. Now let's the xz plane, the zx plane. What is a zx plane? What's the equation for the zx plane? Y equals 0. So when y is equal to 0, you have z is equal to x squared, right? So imagine on your xz plane, now this is a little slanted, so we have to look at it kind of sideways. Imagine on the xz plane you have z is equal to x squared. Now if you just change those variables to y and x, then it kind of just looks like a parabola. So this is kind of a parabola that's sideways. And how about the yz plane? What's the equation for the yz plane? X equals 0. When x is equal to 0, you have z is equal to y squared. That looks like on the yz plane, it would be a parabola. So imagine two wire parabolas going on the xy, on the xz, and on the yz planes. And then, so what do you think would happen to everything else? Well, we tried to see what happens when z is equal to 0. Let's try to see what happens. You know what the plane z is equal to 1 looks like? It's what? It's flat. It's horizontal, except it moves up when z is equal to 1. So when z is equal to 1, what do you think is going to happen here? 1 is equal to x squared plus y squared. What is that? That's a circle, radius 1. So if you move up 1 unit and slice this surface, it's going to have a cross-section of a circle, right? If you go up and z is equal to 2, that's another circle with a radius of square root of 2, whatever that is. But the point is that it's just another circle. So you see what's happening here? Do you see the picture that we're eventually going to get? It looks like a little bowl cup thing, right? It's a surface. And so that's how it's going to look like. So this is called an elliptic paraboloid. Actually, this is more of a circular paraboloid. And what would an elliptic paraboloid look like? Or let me ask you this. What would the equation of an elliptic paraboloid look like? Z is equal to x squared over a squared plus y squared over b squared. So if you just change the radius on one of those lengths, then instead of circles, you'll have ellipses, and it would still be a paraboloid going up. So that's why it's called an elliptic paraboloid. Okay? And then for the x and the y's, if you change the x to x minus x naught, the y into y minus y naught, and the z into z minus z naught, then you would just be shifted around somewhere in space. All right, you don't need to see an official graph of that, right? My picture looks so awesome anyways.
By changing the to change the orientation,
oh, yeah.
we just switch out the variables, so then it would be y equals to x squared over a squared plus b squared over c squared.
Yeah, so in conic sections, if you switch to variables, then the orientation goes sideways. So the same thing happens over here. If you change this into y equals x squared plus z squared, for example, which way is this going to be opening up? Along the y-axis, right? And if the y is negative, then it opens up in the negative y-axis. So this would be a sideways parabola on the y-axis, or paraboloid. Okay. All right. Now, all we said about the paraboloid is that one variable is not squared, the other two are squared. But I didn't mention the pluses and minuses business. So imagine what would happen if you had z is equal to x squared minus y squared. Let me put it this way. If they were both minuses, then that would just be a paraboloid going down. But now, if one of them is a plus and one of them is a minus, what's going to happen? What? It will be in a hyperbolic paraboloid. So let's take a look at it, and let's go through the same process that we did here. I was going to start with z is equal to 0, but let's start with the xz plane and the yz plane first. So on the xz plane, we have, which one's equal to 0? We have y is equal to 0, right? So for the xz plane, y is equal to 0, so I have z is equal to x squared. So that looks similar to the one I had before. Now for the other one, this is where it gets weird. On the yz plane, x is equal to 0, so I have z is equal to negative y squared. Whoa. That's different now. It didn't go up like it did before. This one, I have a parabola. Imagine those two parabolas that you had. One of them was going up, or both of them were going up, those two wire parabolas. And then you change one of them to go down. Now what do you have? I don't know. Let's see. Now let's analyze the slices, the cross sections along those flat horizontal planes, starting with maybe z is equal to 0. When z is equal to 0, I have x squared minus y squared. Oh, how can we negotiate that? What is x squared minus y squared? Well, if I take x squared minus y squared is equal to 0 and send the y squared to the other side, I have x squared is equal to y squared. And if I take the square root with a plus and minus, what do you think I get? Or x equals plus and minus y. If you take all those combinations, a couple of them are going to be the same. So x equals y, and x equals negative y, or if you write it backwards. So you basically get an x. Well, I mean, two lines that are passing through the origin. Okay, fine, whatever. Z is equal to 1. 1 is equal to x squared minus y squared. What kind of graph is that? Let's bring it, we're bringing it down to 2 dimensions. What kind of graph is this? Not an ellipse. Hyperbola. Hyperbola. Oh, hyperbolic. Hyperbola. This is a hyperbola, right? I don't really care at this point. I don't really care which way it opens, but we can easily find that, right? If we let x equals 0, x equals 0, that's the y-axis. I don't see anything happening here. I have 1 is equal to negative y squared. That's not going to happen. So when y is equal to 0, that's the x-axis. So I know it's going to be opening this way. It's harder to draw these things here. That's why I'm kind of not drawing it here. I'm just looking at it from a flat point of view. Let's switch it so that z is equal to negative 1. Now this is just another hyperbola, but this time it'll be opening up on the other side. All right. I don't know if this is helping us much, but and this is really kind of difficult to draw, but what's happening here is that you have this part of the parabola going up and this part of the parabola going down, and everywhere else in between. I can't even draw it. Yeah, that's what the computer's for. This shape is sometimes called a saddle. Imagine what a saddle looks like. You're riding a horse, right? On the bottom side of the saddle goes down around the horse. And on the top side of the saddle, you're sitting on the saddle. So it has that parabola going up where you're sitting, and on a different orientation, the parabola going down for the horse. You see that? Can you picture that? What else do you think is of that shape? Here, take one or more and pass it around. I also, somebody said sun chips last time, so I got sun chips too. If you guys want some sun chips. So, a saddle has that point or has that shape where it goes up from one perspective, goes down on another perspective. And that's what computers are for, right? So let's take a look at the computer. Yeah. So a hyperbolic paraboloid is an example where z is by itself, and so I can graph this as what they call as a function. So let's graph z is equal to x squared minus y squared. So if you look at this, you can see why they call it a saddle. That's not very good. The picture on the screen is not as clear as what I'm seeing here. So it's looking at it from one perspective. We're looking at a parabola going down. Look at it from another perspective. We see a parabola going up. And the hyperbolas come in when you take the slices along the z. So let's see if I can make the slices along the z. Show trace. Ah, I thought it was there. Show. slices, grid axis, format axis, edges, surface, make surface transparent. I don't know if that's any better. Projection. Contour plots, draw contour plots. Sure. Oh, come on. I can't see it at the same time. Show level plan. I can't see it at the same time. So the idea is that if you cut this surface on the horizontal, well, with a bunch of horizontal planes, you'll see these as your result. And let me see if I can actually animate it even better. So z is equal to x squared minus y squared. And this is your graph. And then let's say z is equal to a, let's make a slider. So imagine taking this and slicing it with a plane, and the plane is of varying heights. So if you look at it from the top, you'll see kind of like where they intersect. Maybe I'll make this plane yellow. You can see they intersect here at a hyperbola, and then if I move this exactly at 0, you kind of see those two x's, the x equals y and x equals negative y. And then if we move it further up, you'll see it's a hyperbola opening up the opposite direction, the other direction. And so this technically is called a paraboloid because it has one variable that's not squared and two variables that are squared. So that's the feature of a paraboloid. Now its cross-sectional cuts are hyperbolas. That's what makes it a hyperbolic paraboloid. If I change this into a plus, you know that that's an elliptic paraboloid. And if we take a look at the cross-sections, it looks like they're a bunch of circles. Or if I change one of them, then it'll be an ellipse or something. But in any case, here, let me just change this into something else so that it kind of looks like an ellipse. So this is an elliptic paraboloid because your cross-sectional cuts are ellipses. Okay? So that's your big difference. That's your main difference between an elliptic paraboloid and a hyperbolic paraboloid is what happens when you cut them horizontally. Your result is either going to be an ellipse or a hyperbola. Okay? Now the last thing is a hyperboloid, and unfortunately a hyperboloid is a little bit more complicated because there's two types of hyperboloids. There's a hyperboloid of one sheet and a hyperboloid of two sheets. And we have to talk about cones a little bit. And so between those hyperboloids of one sheet and two sheets, there's some distinctive feature that we need to try to identify, and we'll dig that up. We'll pick that up next time. Okay? Any questions? So do you know what your quiz is going to be tomorrow? I told you yesterday. I forgot. Oh, what's it going to be? Vectors. It's going to be on vectors. Dot products, cross products. Yeah. Tomorrow. Dots, cross, projections, parallelograms, parallelepipeds, stuff like that. Yeah. But there's no lines and planes yet.
Yeah. So chapter
12 up to 12.4.
Up to 12.4.
Yeah. All right, good luck.
Would you like to buy some more pizza before I leave?
Nah, I'm good.